Looks like we're on. I don't see anybody on the Zoom meeting. But I started this meeting. So this will at least be recorded, I guess. I guess we'll just proceed.
It says that there's a bunch of people on the link that you gave us in the email. It looks like everyone's on.
Yeah, so they're not showing up here.
I don't think it's the same link because I don't see you on here.
Can you see this meeting?
There's just nothing on the screen.
Maybe compare meeting ID. Like the numbers.
It's not on.
No, there wasn't any. There's nobody on the screen.
So
There's no post in here.
I think what I might need to do is so copy this. And then let's see. Send an email. Whoops. All right. Now I have to go back and copy that again. So when I get in a hurry, I make more mistakes. So copy a link. Did you get that email? So we're at least going to get the recording, if nothing else. Okay, we'll continue then with section 7.4, integrals of rational functions by partial fractions.
Yeah, this one's working.
Is it online?
Yeah.
Okay. Okay, if you're just joining the other Zoom meeting, I tried to start the scheduled meeting, but it started a new meeting, evidently. Okay, so we're in case 3, integration using the partial fractions method. Okay, so we're integrating rational functions where the integrand is p of x over q of x. And we're assuming that it's a proper rational function. Case 3, the denominator q of x has irreducible quadratic factors, none of which are repeated. So an irreducible quadratic factor has the form ax squared plus bx plus c, where a does not equal 0, and the discriminant is negative, b to the second minus 4ac is less than 0. So that just means that if it's an irreducible quadratic factor, it cannot be factored over the real numbers. So here's an example. Let's find the zeros of this irreducible quadratic factor, x squared plus 4x plus 10. So the way to find the zeros of a polynomial is to set the polynomial equal to 0 and then solve for x. The solutions are the zeros. So solve for x. We can use the quadratic formula to solve this for x. We can also solve it by completing the square. So if we use the quadratic formula, a is 1, b is 4, and c is 10. So we write x equals negative b, which is negative 4, plus and minus the square root of b squared minus 4 times a times c, all divided by 2 times a, or 2 times 1 in this case. So when we do the arithmetic, we get negative 4 plus and minus the square root of 16 minus 40, which is negative 24, all divided by 2. And then remember that the square root of a negative involves the imaginary unit I, which is the square root of negative 1. So we'll simplify this a little bit more. We get negative 4 plus and minus 2 times I times the square root of 6 divided by 2. And let's take it one step further. The 2 zeros are negative 2 plus and minus I times the square root of 6. Okay, so we could write the linear factors of x squared plus 4x plus 10, but they involve non-real numbers. So we say that x squared plus 4x plus 10 is irreducible in the real numbers. Okay, so back to the partial fraction decomposition. Suppose q of x has one irreducible quadratic factor, ax squared plus bx plus c. where the discriminant b to the second minus 4ac is negative, then the partial fraction decomposition will include this expression, ax plus b over ax squared plus bx plus c. So the capital A is distinct from lowercase a, and capital B is different than lowercase b. But this will be part of the partial fraction decomposition. And we know how to compute integrals of rational functions of that form. We've seen a few examples of that already. Okay, so let's take a look at this particular indefinite integral. The indefinite integral of x squared plus 2x plus 1 over x minus 1 times the irreducible quadratic factor x squared plus 9. So first we can write the rational function x squared plus 2x plus 1 over x minus 1 times x squared plus 9. X minus 1 is linear, so we'll just write a over x minus 1. But the other factor is irreducible quadratic x squared plus 9. So in the numerator, we write bx plus c with the denominator x squared plus 9. Okay, so now we want to determine what the values of a, b, and c are. So now we proceed the way that we did yesterday. We'll multiply both sides of this equation by the denominator, x minus 1 times x squared plus 9. So when we multiply the left-hand side by the denominators cancel. So we're just left with x squared plus 2x plus 1. And on the right-hand side, the x minus 1 factors cancel, so we'll get a times x squared plus 9. And then multiply the denominator by bx plus c over x squared plus 9. The x squared plus 9 factors cancel, so we get bx plus c times x minus 1. So I think what we'll do is we'll just expand everything on the right-hand side. We'll get ax squared plus 9a. And then bx times x is plus bx squared. And then plus cx minus bx minus c. So we'll combine like terms. Ax squared plus bx squared is a plus b times in quantity times x squared. And then the x terms, cx minus bx, we'll write that as the quantity c minus b times x. And then the constant, 9a minus c, so plus 9a minus c. Okay, the coefficients have to match. On the left-hand side, the coefficient of x squared is 1. On the right, it's a plus b. So that means a plus b equals 1. The coefficient of x, those have to match. On the left, the coefficient of x is 2. So C minus B equals 2. And then the constant has to match. 9A minus C has to equal 1. Okay, so we have 3 equations with 3 unknowns. The equations are dependent, it appears. So that means it's possible to find the values of A, B, and C. So I guess I'll start with the middle equation. I'll solve for C. So C is equal to B plus 2. And then in the third equation, I'll replace C with B plus 2. So we get 9A minus C, so minus B minus 2 equals 1. And then add 2 to both sides, we get 9A minus B equals 3. All right, the first equation, A plus B equals 1, and this equation, 9A minus B equals 3. So if I rewrite those, A plus B equals 1, 9A minus B equals 4. I can add those 2 equations, and the B will be eliminated.
Sure.
9A minus B equals 3.
What's that?
9A minus B equals 3.
This one?
Yeah.
It's wrong?
It's wrong over here.
Oh, yeah. Yeah, right. Yeah, okay, so then add these equations, A plus B equals 1 to 9A minus B equals 3. The B's cancel. We get 10A equals 4. Then divide by 10, A equals 4/10, which is 2/5. Okay, and since A plus B is equal to 1, replace A with 2/5, so we get 2/5 plus B equals 1, so B equals 3/5. So we're making progress. A is 2/5, B is 3/5. And then to find C, C is B plus 2, or 3/5 plus 2, which is 10/5, or 13/5. Okay, I'll bring out another piece of paper here, but let's just summarize. We have A equals 2/5, B equals 3/5, C is equal to 13/5. Okay, so I'm going to rewrite the indefinite integral that we're working on. Okay, so this is the indefinite integral that we started with. So remember we had a over x minus 1, and a is 2/5. And then plus bx plus c over x squared plus 9. So b is 3/5 and c is 13/5. So we'll look at this individually. We can write the indefinite integral of 2/5 over x minus 1 as 2/5 times the indefinite integral of 1 over x minus 1 dx. Then for the other one, I'm going to write two separate
What the fuck?
definite integrals that are added. So one is plus 3/5 times the indefinite integral of x over x squared plus 9 dx. And then the third one plus 13/5 times the indefinite integral of 1 over x squared plus 9 dx. Okay, we know how to evaluate each one of those. So the one on the left, the indefinite integral of 1 over x minus 1, what's that? Natural log of x minus 1, right? So this is just 2/5 times the natural log of the absolute value of x minus 1. For the middle integral, we can use the substitution rule. So think of u as x squared plus 9, and du is 2x dx. So we need to alter this a little bit. We need to multiply the integrand by 1 in the form 1/2 times 2. So I'll just write this as 3/5 times 1/2 times the indefinite integral of 2x dx over x squared plus 9. So we'll complete this in the next step. And then what about the next one, the third integral? 13/5 times 1 over x squared plus 9 dx. Okay, for this one, we'll use a trig substitution. So let's let x be equal to 3 times tangent of theta, which means dx will be 3 times secant of theta squared d theta. So we'll keep that in mind. Let's go ahead and evaluate the middle integral. So the left one is already finished, 2/5 times the natural log of x minus 1, plus 3/5 times 1/2 is plus 3/10. And what is the indefinite integral of 2x dx over x squared plus 9? We can go into more detail if you want. So I'm getting all scattered out, but let's look at this indefinite integral in isolation. Say indefinite integral of 2x dx over x squared plus 9. So using the substitution rule, if I assign u to be x squared plus 9, then du is 2x dx. And then we substitute 2x dx is du. In the denominator, x squared plus 9, that's u. And the indefinite integral of du over u, natural log of the absolute value of u. And then we put u back, x squared plus 9. So x squared plus 9 is always positive if x is a real number, so we don't need the absolute value symbols. We can just write the natural log of x squared plus 9. Okay, and then we multiply it by 3/10 up here. So this becomes 3/10 times the natural log of the quantity x squared plus 9. Okay, now let's focus on this one, the indefinite integral of 1 over x squared plus 9 dx. We're going to use the trig substitution. So let's just, down here, let's just do that separately. And then when we find that indefinite integral, we'll multiply it by 13/5 and include it in the answer. Okay, so down here, let's just start over with the indefinite integral of 1 over x squared plus 9 dx. So we pick x to be 3 times tangent of theta, and dx is 3 times secant of theta squared d theta. So we make substitutions. For convenience, I'll just put dx in the numerator, since dx is in the numerator. So we get 3 times secant of theta squared d theta. And then replace x with 3 times tangent of theta. So x squared is 9 times tangent of theta squared, and then plus 9. Okay, I'll write a little more detail than is absolutely necessary, but we get 3 times secant of theta squared d theta in the numerator. Factor 9 out of both terms in the denominator, so 9 times the quantity tangent of theta squared plus 1. And then tangent of theta squared plus 1 is secant of theta squared. So 3 times secant of theta squared d theta over 9 times secant of theta squared. Secant of theta squared divided by secant of theta squared is 1. 3 divided by 9 is 1/3. So I get 1/3 times the indefinite integral of d theta. So we get 1/3 times theta. And we determine what theta is by our trig substitution. So remembering that we have x equals 3 times tangent of theta, we solve this for theta. First divide both sides by 3. X divided by 3 equals tangent of theta. And then the inverse tangent or arctangent, inverse tangent of x over 3 is equal to theta. So our integral here is 1/3 times the inverse tangent of x over 3. Okay, then in our original problem, we're going to multiply this by 13/5, but I'll go back to where we were. So 13/5 times 1/3 is 13/15. So our third integral is plus 13/15 times the inverse tangent of x over 3 and plus a constant. So if you can read my writing, this is the answer to our integral. All right, so to reiterate this particular case, the denominator has non-repeating irreducible quadratic factors. So x squared plus 9 was in this case, is the only irreducible quadratic factor. And the partial fraction decomposition involved bx plus c over x squared plus 9. Hey, let's take a look at case 4. Okay, case 4, the denominator q of x has a repeated irreducible quadratic factor. Okay, so suppose q of x has the irreducible quadratic factor ax squared plus bx plus c raised to the power m. So that means the partial fraction decomposition will include a sub 1 times x plus b sub 1 over ax squared plus bx plus c plus a sub 2x plus b sub 2 all over ax squared plus bx plus c to the second, and so on and so on and so on. The last one is a sub m x plus b sub m divided by ax squared plus bx plus c to the power n. So it looks pretty ominous if that ever happens. So we have a fairly simple example, but it's going to be enough work as it is. So in the denominator, we have a repeated irreducible quadratic factor, x squared plus 2 squared. Okay, so we'll write down our partial fraction decomposition 4 over x times x squared plus 2 squared. We have a linear factor x, so we'll write a over x. And then the irreducible quadratic factor x squared plus 2. In the numerator, we'll have bx plus c over x squared plus 2 to the first, or just x squared plus 2. And since it's repeated, the third partial fraction will be dx plus e over x squared plus 2 quantity squared. And then we'll use the same method to determine the values of capitals A, B, C, D, and E. Just like we did before, we'll multiply every term on both sides of the equation by the common denominator, or by this denominator. So when we multiply every term on both sides by the denominator, x times x squared plus 2 squared, on the left-hand side, we'll get 4. This term, a over x times the denominator, the x's will cancel, so we'll get a times x squared plus 2 quantity squared. And then when we multiply bx plus c over x squared plus 2 by the denominator, one factor of x squared plus 2 will cancel. So we'll get bx plus c times x times one factor of x squared plus 2. And then finally, the third term, the x squared plus 2 squareds cancel, so we'll just be left with the quantity dx plus e times x. Okay, we'll expand everything on the right. So the left-hand side is just the constant 4. When we square x squared plus 2, we'll get x to the 4th plus 4x squared plus 4. So in this next step, I'll just multiply bx plus c times x and write it as bx squared plus cx times x squared plus 2. And then on the right, multiply dx plus e times x. Whoops, this should be a plus sign. Plus dx squared plus ex. Okay, we'll begin the expansion a times this quantity. So a times x to the 4th plus 4a x to the 2nd plus 4a. And then bx squared times x squared is plus bx to the 4th plus c times x squared is plus cx to the 3rd. And then plus bx squared times 2 is plus 2bx squared. And then finally, plus cx times 2 is plus 2cx. And then we have dx squared plus ex on the end, plus dx squared plus ex. Okay, now we'll collect like terms. Two terms have x to the 4th, ax squared, ax to the 4th times bx to the 4th. So we'll write that as a plus b times x to the 4th. Just one term has x to the 3rd, so we have plus c times x to the 3rd. Then the x squared terms, we have 4ax squared plus 2bx squared plus dx squared. So when we group the coefficients, we get 4a plus 2b plus d x squared. Okay, then the x terms. So there's just two terms with x in it, plus 2cx plus ex. So we'll write this as plus the quantity 2c plus e times x. And then there's just one constant plus 4a. Since the left-hand side does not have an x to the fourth term, it must mean that the coefficient a plus b is 0. A plus b is 0. The left-hand side does not have an x to the third term, so, and there's only one x to the third term here, so this means c is 0. The left-hand side does not have an x squared term, so this coefficient, 4a plus 2b plus d, that's also equal to 0. The left-hand side does not have an x term. We already know that c is 0, so that must mean e is also 0. Okay, so we know what two of those numbers are. C is 0 and E is 0. And then the constant 4 equals 4a. 4 equals 4a. So now we know that a is equal to 1. Okay, so we're making some progress. Okay, since a is 1, we can determine what b is because a plus b is 0. So replace a with 1. 1 plus b is 0, so b is -1. Hey, there's only one number left to find, that's d. But since we know that a is 1, so we're looking at this equation to find d. Replace a with 1, so 4 times 1 is 4. B is -1, so 4 plus -2 plus d is 0. So 2 plus d is 0, that means that d is -2. Okay, I'll rewrite this integral with, and then substitute a, b, c, d, and e with those numbers. So you won't be able to see this for a second. I'll just write it down real quick. Yeah, I'll slide it up in a second after I write it. So you can just focus on that for now. I'm just going to replace a with 1. And so on. So with those substitutions, this is what I get. I could have made it more nice if I had written minus x over x squared plus 2. But we're okay. So we know how to compute the antiderivative of 1 over x. That's the natural log of x. We're going to use u substitution for each of those. So it looks like we don't need any trig substitution this time. So I'm going to do a little bit of alteration on this, and then we'll compute the indefinite integral all at once. So 1 over x. And then I'm going to write minus 1/2 times 2x over x squared plus 2. And then here I'll just write minus 2x over the quantity x squared plus 2 squared dx. Okay, so this middle term, 2x over x squared plus 2, that has the form du over u, right? Because if u is x squared plus 2, du is 2x dx. And the third term, this has the form du over u squared, because if u is x squared plus 2, du is 2x dx. So we're all set to evaluate this. The indefinite integral of 1 over x is the natural log of the absolute value of x. And then minus 1/2 the natural log of x squared plus 2. And then minus, well, we're going to get one over negative x squared plus 2 to the first. So just to remind you, if you have something like du over u to the second, this is u to the negative 2, the integral of u to the negative 2 du. And then we add 1 to the exponent and divide by the same number. So it turns out to be u to the negative 1 over negative 1, or negative 1 over u. So that is what I depicted here. This is the negative of 1 over u. So if you just make those plus signs, then we have our indefinite integral. Okay, so it looks like we're about out of time. We did see examples of all 4 cases of the partial fractions. So I guess that's all for today. Well, it looks like people were able to get online.